Today we're looking at the chain rule, and I started an example of it last class, so I'm just going to start over there. So let's take example we looked at. Actually, let's look at a slightly more complicated example. I'm going to take the sine of x squared, and I want to know what its derivative. So this is my f of x here. Now the problem is that x squared inside, that's a bit of trouble because we tried to ignore that the other day and take a derivative and we didn't get the right tangent lines. So I'm just going to rewrite this a little bit and I'm just going to make it a little simpler. For a second, I'm just going to say, hey, let's call that u instead of x squared. And this is a common pattern in mathematics where we have some complicated thing and we just do a substitution. We say, let's just replace it with a single letter and see what happens there. So this is what's called the U substitution, and we're going to do this more and more throughout this course and the next one. So now I've got this function called the sine of u, and I want to find its derivative. So the derivative of this with a u inside would be the derivative with respect to u. And I know that the derivative of the sine is the cosine. And as long as the variables match here and here, it just is a u. That's it. And then yesterday I mentioned what's called the differential form of this, where we separate the du from the rest of it. So the derivative of the sine of u can be thought of as the cosine of u times this thing called du. And du is just an infinitesimal change in the variable u. And that's related to our limit that we get close to but don't touch 0, which means we're talking about these like subatomic particles. Is kind of an interesting way to think about them, these unbreakable little particles. All right, so that's that. But I can take this a step farther by saying, okay, but u is really x squared. And I could take the derivative of u with respect to x, and that, according to the power rule, is just 2x. And then I can rewrite that in differential form. So now I have du is equal to 2x dx. And then I can put all of this together. So to put it all together, I'm just going to take back this statement right here. So the derivative of the sine. And this time, instead of putting the u in there, I'm just going to say, hey, let's use that substitution right there. U is x squared. They're interchangeable, so I can put an x squared there. Now, based on calculus, I know that if u is x squared, then du has to be 2x dx. So this du outside here, so on the other side, so I'm getting ahead of myself, I got to write my equals, I got my cosine. Instead of a u, like here, my u is an x squared because I made this statement up above. And then instead of the du, I now have this other substitution that says du is really 2x dx. And if I want, I could bring that dx to the other side. So the derivative with respect to x of the sine of x squared is equal to the cosine of x squared plus 2x. Oops, no, times 2x. And so we're going to check to see if this is really true and that this algebraic trickery isn't just false. And the main way we have to check something like this is to say, well, does this really produce slopes of tangent lines for that function up there? So let's just graph and check. So let's get, now I know we could just use something like the derivative calculator, but that's not nearly as much fun playing with pre-graphs. All right, so I got my original function, f of x equals the sine of x squared. And the other nice thing about this is I view math as an exploration, and so this is a lovely exploration tool someone made for us. All right, so that's the function right there, and let's say we're going to play around with what's going on at x equals 1. We want to try and find that slope there. And we think the slope function, let's call that d of x for derivative, is the cosine of x squared times 2x. And I don't really want to see it. It's kind of cool looking that way. All right, So I think that's my slope function, and I'm interested in the point 1, comma, f of 1. So there, GeoGebra graphs it for me, and I want to find the tangent line there, and so I'm just going to use the point slope form for that, which would be y minus my y value, which is f of 1, equals the slope, and sorry, the word is off balance, there we go. And the slope, well, that's my derivative evaluated at 1. And then we multiply by x minus our x value, so that'd be x minus 1. And I typed that correctly. There's a tangent line. Ooh. Zoom in and see if it's actually a tangent. So I'm only concerned about that place A there. And it's having a little trouble zooming because this is a complicated function, right? Every time we zoom, it has to redraw all of these points that make that. Yeah, so if we just zoom in right there, that looks pretty good as a tangent line. That's the slope of the function at that point. So it looks like I do indeed have the correct derivative function there. So the next step is we'll do another example like this, and then we'll look at how to generalize this procedure for any pair of functions. So let's try a different one. Let's go slightly easier. Oops, wrong button. There it is, new page. Let's take f of x equals 5x minus 7 raised to the third power. So the only way we have to do this before today is to multiply this out. So if we wanted to take this derivative, we would have to take 5x minus 7 times 5x minus 7 times 5x minus 7. And we could either apply the power rule 3 times in a row, or the product rule 3 times in a row, or we could multiply all of that out and get a single polynomial. And either of those is a significant amount of work, but it's not too bad. So what I'm going to do is I'm just going to rewrite that and just call that u cubed for a minute. Right? So when I do that, I'm thinking let's just simplify this and remove the 5x minus 7 by just calling it u. And then if I were to take the derivative of this with just u as the variable, well, that's just the power rule, which says that's 3 times u to the power 2. And then we use the differential form of that, which says the derivative of u cubed is 3u squared du. And then we come back and say, all right, let's deal with this u thing now. U is really 5x minus 7. And we know how to take the derivative of u with respect to x. It would just be 5. And then write that in the differential form, which says du equals 5 dx. Putting all of this together, I have the derivative of, and I'm going to replace that u right here with what I say it's equal to is the 5x minus 7. So replacing that u with 5x minus 7, and it's cubed, that's equal to, on this side here, I've got 3 parentheses, and u is 5x minus 7. So all I'm doing is putting the u back in here, and then du is really that, 5 dx. Okay, so again, what I wrote there is this is my u cubed here, this is my 3u squared there, and that's my du right there. And so now I have a derivative. The derivative with respect to x, right, divide this over to the other side, of 5x minus 7, parentheses cubed, is 3 times 5x minus 7 squared times 5. And so you can see a couple things happening here when we look at this. The 5x minus 7 just kind of stayed put here, and then we just applied the power rule. And then we had to adjust by multiplying by the derivative of that inner function. right? The 5 is the derivative of 5x minus 7. And that same thing happened back here. I took the derivative of the sine, which is cosine, and the x squared stayed put. And then I had to adjust by multiplying by the derivative of x squared, had to pop out there. And it turns out that is the general rule. That's called the chain rule. And I'll just do the differential proof of it. There's a different proof in the book if you care to read it. So the chain rule says if you have the derivative with respect to x of a function that has another function inside of it, so this is called a composite function, the chain rule says take the derivative of f and leave that inside alone. Then adjust by multiplying by the derivative of that inner function. Right? So f is my outer function. So I take the derivative of the outer function and I multiply by the derivative of the inner function. And that's the chain rule. So I'm going to do the differential proof. Oh, sorry, I missed a chat there. Can the product rule be used more than once in a function? The answer is yes. So after let me do an example, prove this, and then I'll go back and address Kelsey's question, which was, can I really apply the product rule to all of that right there? And the answer is, yeah, you can. And I'll show how. All right. So the proof of this is just to use the U stuff I was talking about. So if I just look at f as f of u, and I take the derivative of that with respect to u, and so note here I'm saying that g of x and u are the same thing, but I'm just doing this substitution to make things look slightly easier. Then that's what we're going to call f prime of u here. And then we can move the differential over to the other side. So the differential form says the derivative of f of u is equal to f prime of u du. All right, so just using a different variable, that's what a derivative is. And then we come back in and we say, all right, but u is equal to g of x. So that means du dx, the derivative of u with respect to x, well, that's just g prime of x, because these are two ways to write the derivative. And then we can rewrite that in differential form that says du is equal to g prime of x dx. And then we're just going to take our u equals gx and our du equals g prime, and we're just going to substitute them back over there. So now I've got the derivative of f, and instead of u, I'm going to put back the g of x in there. On the other side, I have f prime. And what is u? U is really g of x, so I put the g of x back in. And du is really all of that, and so I have to multiply by g prime of x dx. And so this right here is the differential form of the chain rule I wrote above. We could easily just take that dx and divide it back to the other side, and it's a match. So here's the chain rule in standard form, and here's the chain rule in differential form, and they're pretty much identical. So let's see, Cole's threw another question there. What if we're doing an equation like sine of x squared over cosine of x cubed? Yes, we'll do that in just a minute. And so now we have an extra rule that allows us to take derivatives we couldn't do earlier at all or couldn't do easily. So for example, this derivative is doable without the chain rule. It's just a lot more work because either I have to distribute all this stuff or apply the product rule twice. And I said apply the product rule twice because there's one multiplication there and another multiplication there. So there's two products here. But this function, sine of x squared, we don't have another way to do that. The chain rule was the only way to find that derivative. So the chain rule is an essential tool in our tool belt now. And I want to go back to this one right here and talk about how the product rule could be used on that, because that's a good exercise and review of the product rule. So I've got this function, f of x, and I'm writing it as 5x minus 7 times 5x minus 7 times 5x minus 7. And my claim is that I can apply the product rule to this. To do that, we have to kind of do it in stages, and then I'll show it without stages in a minute. I'm going to group this together as a single function, and then the multiple is right there. So when I find f prime here, that f prime of a product says take the derivative of the first function. So I'm just going to write it as 5x minus 7 times 5x minus 7. That's my first function right there. And I'm just going to make a note that I need to take that derivative. Multiply that by the second function, which is just that one right there. And then I want to add that to leave the first function alone. So that's just going to be the 5x minus 7 times 5x minus 7. So that's my first function here. Right? I isolated it, times the derivative of the second function. Well, that I can do easy. That's just 5. Now I got to deal with this part right here. What's the derivative of that right there? And then we'll tack the rest of it on. Well, if I apply the product rule to just that part, that says take the derivative of the first function. Well, that's just 5. Multiply by the second function, 5x minus 7. And then add that to the first function left alone. Well, that's just 5x minus 7 times the derivative of the second function, which is just 5. So just a reminder what I'm doing here. I just claimed that this was one piece and that's the other piece. And now I've just taken its derivative and I got to bring this other stuff back in. So now I got to take this stuff and bring it down. So that red parentheses is times 5x minus 7 plus 5x minus 7, 5x minus 7, times 5. And I have a few more extra parentheses that I need. I definitely need, like I don't need the square brackets here, I just put them in there for emphasis, but I do need the red ones here because I have to distribute this 5x minus 7 through there. So distributing that through, I get 5 times 5x minus 7 times another 5x minus 7. And I'm going to run out of room if I don't slide that over. Okay, so I just distributed this there. Now I have to distribute that here. So then I get plus 5x minus 7 times 5, right? That's that, times this 5x minus 7. So that's all of this. And now I have plus 5x minus 7 times 5x minus 7 times 5. And really, these things are all the same, right? This is 5 times 5x minus 7 squared. This is 5 times 5x minus 7 squared. And this is 5 times 5x minus 7 squared. So there's 3 of them there. Oh, my battery's going to die on my tablet. And so I end up with 3 times 5 times 5x minus 7 squared, which is the derivative we found with the chain rule over here, 3 times 5 times 5x minus 7 squared. But I want to point out something really cute here. Check this out. Forget that I called this f up here for a second. And what I want to do here is call this part f, this part g, and that part h. And if I do that, what ends up happening here, and let's pick a different color, this right here is the derivative of that first factor times the other factor and the third factor. Here, I leave the first one alone and I take the derivative of the second one. So that's g prime. and h just stays as it is, right? So this whole thing's f, that whole thing's g, that whole thing's h. And over here, f stayed put, g stayed put, and I multiplied by h prime. So can you see the three function version of the product rule? So essentially, you can generalize the product rule. So the original product rule looks something like this. If you take the derivative with respect to x of some function f times some function g, that's f prime times g plus f times g prime. And it turns out you can just put as many functions as you want multiplied in there. So that extends the derivative with respect to x of f times g times h. And these are all functions of x, is f prime times g times h plus f times g prime times h plus f times g times h prime. So you just take one derivative at a time and multiply by the other functions and then add them all up. And that's kind of a generalized product rule. Isn't that awesome? All right, so let's see. Cole had a good question. Let's go look at that one. Guesses that's a homework question, but I'm not sure. Page. So how would I apply the chain rule to something like sine of x squared over the cosine of x cubed? So I want to take the derivative of that. And it looks like I got to get a plug for my tablet. Hang on a sec. Brief intermission. Need some intermission music. Oh, there maybe. That might reach. Okay, power. So this one right here, I have multiple things going on. I have a quotient, so I'm going to apply the quotient rule, and then the chain rule will apply when I have to take the derivative of the sine of x squared. So I'm just going to write this down in kind of stages. So the quotient rule says take the derivative of the top function. So I'm just going to write derivative of the top function multiply by the bottom function, minus, leave the top function alone, and multiply by the derivative of the bottom function. So there's derivative of the bottom function. And then all of that is over the bottom function squared. So I'm just kind of setting myself up for the quotient rule. So that's what the quotient rule says, right? Derivative of the top times the bottom minus the top times the derivative of the bottom. And the derivative of the bottom always has to go with the subtraction. So that's important that we get that order correct. Now this right here is where I apply the chain rule. And then again, we'll do it over there. So let's break that down. So now the derivative of the sine of x squared, the chain rule says, first, just take the derivative of the sine, which is the cosine, and don't mess with the x squared yet. Then multiply by the derivative of x squared, which is 2x. So that's this right here. And then don't forget, I have a cosine of x cubed sitting there, minus the sine of x squared is just sitting there waiting for stuff to happen. And what happens next is I apply the chain rule here, and the chain rule says, take the derivative of the outer function, derivative of cosine is negative sine, leave the x cubed alone for a sec, and then multiply after by the derivative of x cubed, which is 3x squared. And so sometimes I find it helpful to get the order right here is I have to identify what is the outer function. The outer function here is cosine of whatever, and then what is the inner function? And that's just x cubed. So first take the derivative of cosine, which is negative sine, and then leave whatever it had there. Then multiply by the derivative of the inner, which is 3x squared. All of that is over cosine squared of x cubed. All right, can we clean this up very much? What do we got? Let's get a highlighter. Let's see, well, I have a factor of x here, and there's a factor of x inside that square there. Negative times a negative will clean up a little bit. And then I have a cosine of x squared, but no other cosine of x squared. I have a cosine of x cubed, no other cosine of x cubed. I have a sine of x squared, at least in the top. There's no other sines of x squared, sine of x cubed. Not much happens. All right, so the best so far I think I can do here is factor out an x, and that leaves a cosine of x squared. That 2, I'm going to draw right in front of the cosine. So that, I pulled out the x, and then I have a cosine of x cubed minus a negative plus, and I'm taking one of those x's out, so I'm going to write in front here a 3x, and then I have sine of x squared. So I got that. I got both of those x's accounted for, times sine of x cubed. So now I have that. And all of that is over cosine squared of x cubed. And we can't cancel here because there's a cosine of x cubed here, but not there. This has a 2, that has a 3x. So cosine, cosine, sine, sine looks kind of like the angle sum for cosine, but the 2 and the 3x messed that up. Don't see anything else we can do to clean this up. I mean, if you're dying to cancel here, the best we could do, let's see if I can get this right, page. I think I got that in my head. Let's see. So I have and then I have to put the x back in. Yeah, I have to write this 2x cosine of x squared cosine of x cubed over cosine squared of x cubed plus 3x squared. So I'm putting the x I factored out back in. You just made that up on the spot. Cool, this is a fun one. Thank you, Cole. Times the sine of x squared. Thank you for challenging me this morning. I needed that. X cubed over the cosine squared of x cubed. Let me look back to make sure I got that right. So what I was doing there is I put the x back, I multiplied the x back in here so that I could divide each part of the sum by the cosine squared of x cubed, so then I could at least cancel that, but I don't think that makes my life any better really. So now this cancels with one of those in the square there. So then I've got 2x cosine of x squared. And this goes back to, like, a couple people have messaged me, is this the simplest form of the answer when they were working on their homework? And I'm like, well, I don't know. I'd have to try a whole bunch of algebra and see. The only way to know if something simplifies is to try and see what happens. So here's me trying and perhaps failing. It's not really a failure. I mean, I'm trying. I didn't do anything wrong yet. So at least I get to cancel something. So here's one form of the derivative here. And here's another form of the derivative there. Now this form, I got to factor something out, but nothing canceled. In this form, I got to cancel something, but I had to write this cosine more than once. So like which one uses less ink if we were to weigh this answer and weigh this answer? Man, they look pretty darn close to the same amount of ink to me. It is possible this simplifies a tiny bit more. There might be some obscure identities I don't know about for the cosine of x squared. If you look up trig identities, there's way more than are covered in the standard trig class because the sine and cosine are so wonderfully inbred. They do all kinds of wild things together. We could also, like here, I see a sine over a cosine and another sine over a cosine. Let's see, with the x cubed, we could throw in a tangent here, but then we have tangents and sines and cosines. This has an x squared and an x cubed, so I can't mess with that. They have different innards. Yeah, right. Sometimes things clean up dramatically, sometimes they do not. So this extra work here led me to another simplified answer that is not much better than the simplified answer I have over here. The only way to know is to try. That's life. Math is an exploration. All right, let's try something else. Let's see, what else do I have on my plate to look at? That one, that one. I'm trying to find something reasonably cute. Ooh, that's a good one. Okay. Oops, wrong way. Actually, I'm going to stop here.